right, so we're in section 2.3. We're going to talk about definitions today. And we're not talking about definitions like the definition in a dictionary. We're talking about what makes a definition for math. And it's a little bit different because in math we like lots of details. We like to be very very specific.
Like Mr. Bean, your hair has so much definition.
Mr. Bean, have you ever watched the show Fringe?
No. Let's put the computer away, please, guys. What's that? You should listen to the notes. And it's not about definition in your hair, like they talk about in your ads. So what we talked last week about conditional statements and what conditional statements were if we have an if and a then, and we made the converse of the conditional statements. We switched them around to make the converse, and we figured out that sometimes the converses are not true. Well, what makes a definition a good definition is if we have a conditional and its converse both true. So when we write a definition as a conditional, and conditional, remember, means if and then. So when we write a definition as a conditional, guys, let's go back to our regular seats, please. You can't see from the second row? You should wear glasses then.
I can see better from back there.
No.
So when we write a definition as a conditional, its converse is also true. And this is true, the way we make definitions in math is by having a conditional where the converse is also true. So a good definition a good definition in math is a conditional statement where the converse is also true. So this is how we make a definition in math. We figure out a conditional statement and we make sure that its converse is also true. We write this as P if and only if Q. The other way we can write that is with our double arrows. These both mean the same thing, and this is called a biconditional. So this is how we make a definition in math. We have a conditional statement that talks about whatever we're interested in, and its converse is also true. When our conditional statement and the converse is also true, we can write it as a biconditional, if and only if. So let me write a couple of examples of definitions and biconditionals and the conditionals. So any questions before I change the page here? Okay. So here would be a definition. An angle is a right angle. This is an example. If and only if it measures 90 degrees. That would be a definition of a right angle. An angle is a right angle if and only if it measures 90 degrees. And the way I can split that into two, into a conditional and its converse, I could say an angle is a right angle if it measures 90 degrees. And I can make its converse, if an angle measures 90 degrees, then it is a right angle. And both of those are true. The conditional and the converse are true. So I can split the biconditional into two parts and make it a conditional statement going either direction. Yes.
So now, I don't know if the English will do this, but will there be like definitions that like aren't true?
Well, there might be something where it says, is this a good definition? So an example of that would be, is this a good definition for a square? A square is a figure with four sides. So my condition would be, if a figure has four sides, then it is a square. And the converse would be, if it is a square, then it has four sides. Is the converse true? What would be a counterexample?
Rectangle.
A rectangle. A rectangle has four sides and it's not a square.
Well, you could
So,
say that up there to
so that you would have to say something more, something stronger like that. So that's going to be the kind of question you'd be asking. Is this a good definition? To be a good definition, the conditional statement has to be true and the converse has to be true. That's what makes a good definition. And then you can write it as an if and only if. So let's use the example that we just talked about. A figure is a square. If and only if it has four congruent sides, and what else does it have to be a square? What about the angles? And four right angles. Because we'll talk about a shape called a rhombus that has four equal sides, but the angles aren't all the same. So this would be a good definition of a square. A figure is a square if and only if it has four congruent sides and four right angles. So we could break that into a conditional statement and the converse. If a figure is a square, then it has four congruent sides and four right angles, and we can turn it around. If a figure has four congruent sides and four right angles, then it is a square. So we can say it both ways, and it's true both ways. All right, let's come up with a definition of our own. So let me grab this page here. And we're going to come up with a definition for something called a flopper. Let me make this a little bigger. All right, so here is a picture of some cards, and up here are things that are floppers, and here are things that are not floppers. So what is special about floppers? What do all floppers have? One eye and two legs. And where's the eye?
Right there.
Is it inside or outside? Inside. So all these things have one eye inside and two legs.
On the outside.
Two legs on the outside, one eye on the inside. Okay, so that's good. We're being more specific. These are not floppers. What makes this one not a flopper? Doesn't have any legs. This one has two legs, but it has two eyes. This one, no eyes. So let's look at the ones down at the bottom. Is A flopper or not a flopper? A is not. B, how about B? Not a flopper. What makes B not a flopper? It's got two eyes. What about A? What makes A not a flopper?
It's eyes on the outside and it only has one leg.
Its eyes on the outside and only has one leg. Its eye flew off and it lost a leg. How about C?
It is. It's not. Yeah, it is because it has two legs and one eye on the outside. Oh, no. Wow, Preston.
So it does have one eye inside, but what's the problem? If the leg is inside and it's kind of, is it really not even really a leg, is it? So C is not. How about D?
Yes.
Yes. It has an eye inside and two legs. So D is yes, and E?
Yes.
Yes. So D and E are floppers. So let's write a conditional statement about our floppers. If it is a flopper,
I think your E's are backwards, sir.
someone else said that the other day.
Don't you notice me?
Um,
Yeah, they're backwards.
Who cares?
So I think what happens is I kind of halfway print and my E is almost a strict E. So yeah. So if it is a flopper, then what does it have? It has, what did we decide?
2 legs on the outside and 1 eye on the inside.
2 legs outside. And 1 eye inside. So let's write the converse of this. If it has, how do I write the converse of this?
One eye inside.
If it has 2 legs outside,
Well, I mean, if I lose an eye, I could be a flopper.
and 1 eye, then what's our then here?
Then it's a flopper.
Then it is a flopper. All right, so let's turn this into our biconditional, our if and only if. It is a flopper if and only if it has 2 legs outside and 1 eye inside. So there would be our definition of a flopper. It is a flopper if and only if it has 2 legs outside and 1 eye inside. So based on the information that we have, we came up with a definition for what a flopper is. So here's our definition, our biconditional statement. If and only if is a biconditional. And here are our 2 conditional statements that are combined to make this biconditional statement. So I can take these 2 conditional statements and turn them into a biconditional statement. I can also break this if and only if, this biconditional statement, into 2 conditional statements, a statement and its converse. And I could also put this information in an Euler diagram. Not here. I can put this information into, we'd actually have to use 2 Euler diagrams to make a definition. So one would be for my first conditional statement. Flopper. And my bigger category, or sorry, my smaller category would be 2 legs, and I'm going to make it shorter here, and 1 eye. And I could also write my Euler diagram for the other conditional statement. So this one would be 2 legs, 1 eye. And inside that one would be our floppers. So these 2 Euler diagrams would combine to make my definition for a flopper. It is a flopper if and only if it has 2 legs outside and 1 leg inside. So questions on biconditional statements. Biconditional means if and only if, and it can break into 2 conditional statements. A conditional statement and its converse.
I have a question.
Yes.
How did you come across flop?
This is actually a page from the book. So the reason we're doing this with floppers is the idea is it doesn't matter what we apply it to. It doesn't have to be angles. It doesn't have to be numbers. The idea is how do we make a definition? And a lot of times in math, if you go further in math, you talk about things that seem really abstract. They don't necessarily have to do with numbers. They don't necessarily have to do with angles. You're talking about groups. If it is an abelian group, then such and such is true. And you're dealing with these abstract ideas, but the idea of a definition and how you make a definition is still the same. It doesn't matter what you apply it to. All right, let's come up with another definition. This one does actually have to do with geometry. So we're going to figure out what makes an adjacent angle. All right, so we're going to look at this diagram for adjacent angles and figure out what's important about adjacent angles, and come up with a definition for adjacent angles. So here it tells us that angle 1 and angle 2 are adjacent angles. Here it tells us that angle 1 and angle 2 are adjacent, and angle 2 and angle 3 are adjacent. Here angle 1 and 2 are adjacent, angle 2 and 3 are adjacent, and angle 4 and 5 are adjacent. So right away, before we start looking at what are not adjacent angles, what do you think is important about adjacent angles? So just looking at these pictures, what do you think adjacent angles have to do with?
180.
Well, these 2 don't necessarily add up to 180. I guess it could be 90, but that 1 and 2 don't necessarily, angle 1 and 2 don't necessarily add up to 90 or 180. But that's a good guess. What do you think, John? Well, no, that 1 and 2 here don't have the same measure. Okay, that's good. Next to each other. So that's a good one. Did someone back here have next to each other? Anybody see anything else that's important about adjacent angles? Oh no, that's a different thing. We'll talk about those in just a couple of days. Those are called vertical angles. Okay? All right, so let's look at what are not adjacent angles to try to refine this a little bit. 1 and 2 are not adjacent angles. So they're not next to each other, so that we figured that out. Angle 1 and 3 are not adjacent angles, so they're not next to each other. On this next one it says angle ADB. so that's this angle, is not adjacent to the big angle. So those aren't really next to each other. What would we say is going on with these angles? They're connected. They well, okay. Do all the adjacent angles have the same vertex? 1 and 2, 1 and 2, 2 and 3, 1 and 2, 2 and 3, 4 and 5. Do they have the same vertex?
Yeah.
Okay, so let's write that on there. They're next to each other. They have the same vertex. What could you say these two angles are doing? Are they next to each other? Anybody? They're kind of on top of each other, aren't they? So, or they overlap. So these overlap. One's on top of each other. So adjacent angles are next to each other. They have the same vertex. They can't overlap. Here, angle 1 and 2 are not adjacent, so they're not next to each other. They don't share the same vertex. It says that angle 1 and 2 are not adjacent. They're next to each other, but what's going on with angle 1 and 2 here? What's that? No, I think they're on different planes. This is 3D. So these two adjacent angles are on different planes. So we have to be on the same plane. Now let's look at and see if we can figure out one other thing that's important about adjacent angles. They're next to each other, so if they're next to each other, they have the same vertex. What else are they sharing? Angle 1 and 2, they have this in common. Angle 1 and 2 have this in common. Angle 2 and 3 have this in common. So what do we call that part of?
They all share one line.
And for an angle, what do we call that? The ray that's part of the angle. It was on our first test. The end point is the end of the ray, but the angles have two sides. So they share a side. So the adjacent angles are next to each other. They have the same vertex. They can't overlap. They have to be in the same plane, and they share a side. So let's look here. Are angles 1 and 2 adjacent?
Yes.
Yes? They're next to each other. They have the same vertex, and they share a side. How about angle 3 and 4? Here's the vertex. Here's the side that they share. So would they be adjacent? Yes? How about 4 and 5? Yes? How about 3 and 5? No. 3 and 5 don't share a side. Because angle 3 goes here, and angle 5 goes here. So they don't share a side. All right, I think we have enough information here
Well,
to define an adjacent angle.
but 3 and 4 don't have a side.
Right here. Here's angle 4, and here's angle 3. They share that side that I marked in black. So let's write a definition now from what we figured out here about adjacent angles. So we're going to say angles are adjacent if and only if they share a vertex and one side they don't overlap And we'll not write it down, but we could also say, and they are in the same plane. So we can go ahead and write that down. They don't overlap and are in the same plane. So this is our definition. This would be a definition of adjacent angles. Angles are adjacent if and only if they share a vertex on one side, don't overlap, and are in the same plane. For shorthand, we usually just say adjacent angles are next to each other. But this would be our technical definition of adjacent angles. And we wrote it as a biconditional with an if and only if. And we could break this into two pieces. We could say angles are adjacent if they share, if angles are adjacent, then they share a vertex, one side, don't overlap, and are in the same plane. That would be one conditional statement. And we could say if angles share a vertex, one side, don't overlap, and are in the same plane, then they are adjacent. We could write it as a conditional and as converse. We could break this definition into two pieces. But the important thing to remember about definitions is we can write in math, we can write our definitions as a conditional statement where the converse is true. And when that's the case, we can write it as an if and only if. All right, questions?